Greetings all. This is Matt Roscoe from the University of Montana, and this is a lecture to replace myself in my absence on Section 13.4 on submersed objects, volume, and weight in our course Math 133 Geometry and Measurement for Teachers. As you can see by the left-hand side of my screen, there are only 5 slides here, so majority of what we'll see today is demonstration. But I want to talk about two things. How can we submerge an object and get a sense of volume, and then how can we submerge an object and get a sense of weight? So the first thing to think about is the submerged object's volume. One hands-on way to determine the volume of an object is to submerge the object in a known volume of water and measure how much water the water level goes up. And just remember that 1 cubic centimeter can hold 1 milliliter of liquid. So a cc is the same thing as an ml. Let's take a look here and see how this works out in real life. Okay, so here I have my desk here at the university. Set up an example where I have some water. I hope you can see that all right. It's about right at 700 milliliters. And what I'm going to do is I'm going to submerge something in this water. And the thing I'm going to submerge is this. It's a triangular prism. Now, these are the ones we use in class. I've taped it shut here to make sure that the water doesn't rush inside of it. Because what I want to know is when I put this in the water, how much does the water level go up by? So are you ready to watch? Let's see if I can sort of get us on a plane here where we can see it good. I'm going to put this in the water. You can see the water level is going up, up, up. And if I hold it in there all the way and try not to get my fingers, I think I've set it up pretty well. So there it looks like the water level went up to about 900 milliliters from where it was before at about 700 milliliters. So in other words, the water went up about 200, maybe just a little bit more than 200 milliliters when I submersed the object in water. So what can we tell from that data about the volume of this solid is the big question. So let's just sort of think about it. Well, if the water level went up, so let's just see here. The water level it went from 700 milliliters up to 900 milliliters. So that's an increase of 200 milliliters. Therefore, the object has a volume equal to, I guess, 200 milliliters of water at room temperature. But we know that 1 milliliter is 1 cubic centimeter of liquid. And so we can conclude that this guy is, so the volume, I guess, of the triangular prism must be, I mean, roughly, let's say, so I'm going to make this sort of a rough estimate, 200 centimeters squared. Well, that's kind of interesting. Let's just see if it really is, right? Let's do direct measurement now. So I'm going to get my ruler out here. Sorry, should have had that out earlier. So here's a ruler. Since we're in cubic centimeters, and that should be cubic, not square centimeters, right? Looks like the triangular base is about, it's somewhere in the neighborhood of 8 centimeters. So I'm going to call it 8.1 centimeters. So the volume here we know is going to be the area of the base times the height, which is going to be 1/2 base times height of the base triangle times the height, I guess, of the prism. So I'll say the height of the prism. So the height here of the triangle and the base of the triangle and the height of the prism. Okay, so let's go ahead and figure this out. 1/2, we said the base of the base triangle is about 8.1 centimeters. the height of that triangle is, oh, it looks like it's about 7, I guess, centimeters. 7.0 really, because I measured it to the nearest tenth. And then the last, let's see, it looks like we're about 8.4 as the height of the prism. And let's get the calculator out and see if we're anywhere near our estimate. So let's see, 8.1 times 7 times 8.4, that all times 0.5. And what I get here is a volume of 238 cubic centimeters. And so I can see that while it's not a perfect system, that submersing something in a known quantity of liquid and watching how much the level goes up and down gives you a good sense, a good estimate anyway. You know, if we kind of think of this as accuracy, you know, we could say, well, we were off by about 38 cubic centimeters, and 38 divided by the relative scale, 200, tells us that we were within about 19%, I guess, of the accepted value. So reasonable accuracy, and of course, accuracy would increase quite a bit if we could increase, you know, the accuracy of this thing right here, right? If somehow we had ways of graduating it a little bit closer. I mean, perhaps if we used something that had a little bit better scale on it, like this. But of course, I couldn't fit my triangular prism inside here. So what's really needed is a really big one of these that would allow us to have a finer grade. So I hope that gives you a sense of submersing objects in liquid and how it can be useful in the calculation of an object's volume, or at least estimating a ballpark volume. So here's a really interesting idea that came to us from Archimedes, one of the great mathematicians of the ancient times from Greece. An object that floats displaces an amount of water that weighs as much as the object. Recall that 1 milliliter of water weighs 1 gram at room temperature. And this is the idea that when an object floats, the amount of water that it pushes out of the way to float must balance with the weight of the object in order for it to float. So this has some deep connections to density, right? Because objects that sink, of course, they must be heavier, right, than the amount of water that they displace when they're placed in the water. So yeah, let's take a look at how this looks. Let's take a look at how this looks then on the ground with a real example. So I'm going to switch over here again to my submersed water here. I can see that the water's gone down just a little bit. I don't know if you can see that. Some of it ended up on my I guess on my triangular prisms. We're just under 700 milliliters right now. And I'm going to take this weird shaped object. It's a piece of wood that I'm going to just put in here and see if it floats. And indeed it does float. And when it floats, I can tell it's floating because I can see down at the bottom it's not sitting on the bottom of the container. So it's just barely floating there. And I can see that the water level's gone up from just under 700 to, oh, I don't know, what do you think? We're sort of in the, I don't know, 830-ish range, 825. I don't know. It would be nice if we had some lines here to measure, so I'm really guesstimating at this point, but we know at least 100 change here and just a little bit underneath 700. So I'm going to call it, let's say 690 to 820. Okay, 690 to 820 when I put this wooden block in there. Okay, so let's think about what that means according to Archimedes' principle. So water level, again, what did it do for a floating object, right? So this object went from just under 600, I think we said 690 milliliters, up to I think we said just over 800, so we're going to call it I'm going to call it 830 milliliters. It was sort of a third of the way. So if we kind of think about the change here, we had an addition in volume of, let's see, 140 milliliters. Now, Archimedes' principle says that that the object will displace an amount of water equal in weight to the weight of the object. So 140 milliliters of water weighs 140 grams. And since this was the amount that was displaced, the object must weigh about 140 grams. And of course you're thinking, well, so what? Let's just see if it really works. So I happen to have a very accurate gram scale, I guess, measuring instrument here. Can you see that? Yeah, it looks like you can see the 00. And the big question is, does this thing really weigh 140 grams? Now I'm going to wipe it off a little bit because I don't want the water to influence the weight of the object actually. And here we go. Drum roll, please. Ooh, 155.5 grams is what we get. So actual weight, 155 grams. Boy, that was fairly close. We were off by about 15 grams on a scale of where 140 was the whole. So 15 divided by 140. So we were within 10% of the actual weight of the object. Again, there's some error here associated with measuring the displacement. Probably a more accurate, weight here given by the actual scale. But I guess the idea is that floating objects can also, measuring the displacement of floating objects can also give you information about an object's weight. And that's really it today. Maybe what we could do is think about one concept question, make sure. So suppose that the water level goes up by 380 milliliters when a toy is placed in the water. How much does the toy weigh? And I'll leave that one for you to ponder. And hope you've enjoyed the video and learned a little bit about volume and weight when objects are submersed in water.